All right, after block day, which I continued to spend building out a block game, which was really fun. Why do we have this top bar? Quite literally do not want this top bar. All right, we're good. Day 23, a long walk. The elves offer to help you go over the edge of the island. Water isn't reaching the ground, it's being absorbed by the air itself. You'll finally have a little downtime while the moisture builds up to snow producing levels. Why not take a walk? Puzzle input is hiking trails, paths, forest, and steep slopes. I guess steep slopes are going to cost. You're currently on the single path tile in the top row, here. Your goal is to reach the single path tile in the bottom row. Because of all of the mist from the waterfall, the slopes are probably quite icy. If you step onto a slope tile, your next step must be downhill, in the direction the arrow is pointing. To make sure you have the most scenic hike possible, never step onto the same tile twice. What is the longest hike you can take? The longest hike you can take? In the example above, the longest hike you can take is marked with O, starting as S. So through here, no repeating basically, which is good for path algorithms, but they don't usually look for the longest path. This hike contains 94 steps. So I guess we could just do this recursively and then check out part 2. Basically breadth first search. It looks like there aren't many options, so we're only going to fork off a couple of times. Our input looks pretty big. There's the input. Okay, the input looks pretty big, probably like 100 by 100 if I had to guess offhand. Doesn't seem too bad. I don't think there's a longest path algorithm. Why is this anyway? Let's not full screen this. There we go. Just create day 23. 23. Dang. What was it? Today, tomorrow, and then the 25th. Wow. Almost done. So all of this, we obviously need to parse this into a grid. We've already written that code. We can get it from another day. I think we'll just have to modify it slightly to get these slopes. So I guess we start with that. Start with the parsing. We need to get our starting and ending spots as well after the parsing. So let's get our parsing in. This hike contains 94, and apparently there's only 1, 2, 3, 4, 5, 6 options total here. So let's figure it out. I think we've called it parse grid in the past. So day 16, 17, 10, 21 all have grids. This is the mirror day. Is the mirror day the best one to pick? I feel like the mirror day might be the best one to pick because it has directions and it has all these mirror types. So I think we can just grab this parser from the other day, and then I'll keep all of the extra stuff, right? And I think that'll be it. Then we'll do the parse. Maybe we'll come back for the row count and the column count or something like that. So I'll keep that open, but I'm going to dump this in here to start. This is obviously not going to be mirrors, and we need glam and nom locate as dependencies. So we'll grab those, and then we don't have mirrors. We have, I don't know, I'm going to call them plots. A directional plot or an empty plot, I guess. Directional plots hold direction, right? Because we've got direction. It's either north, south, east, or west. We will keep those as ivex in the right direction. And then I think that's fine. Ignore hashes, grab arrows. I guess it's carrots, V's. And we're at the top of the hill, so there's no N-ish character. Accurate. So right, down. Is there a left? Oh, all of these. Okay, there we go. So direction, we already have the ivex. This is going to be plot. Let's call this plot type. And then these return plots. All of these need to be adjusted. So we've got 4 directions, right? Let's say we've got up here, right here. We don't need the raw string because it's not a backslash anymore. Down and left. Then we get the spans. Rename all these plot. This is plot type, directional, direction north, directional, direction east, directional, direction south, and directional, direction west. So that'll give us everything. Parser could be cleaner, but I don't really care right now. So we get each one of these, and many one, delimited, dot or new line or hash. Same thing for the other one, dot or new line or hash. And then dot is just this again with a dot and a plot type of empty. So if that goes well for us, then we should have input and a grid from our parse grid. On the input, should parse a grid input there. This input is not going to get used to do, and let's get a debug on the grid at least. We should probably get the print grid too from day 16. I think we wrote one, right? Here's a print grid that matches. We'll bring hash set in. Do we want a hash set is a question. Haven't really even thought about it. I think when we don't just need contains, right? So a hash set of ivex2s isn't enough for us to determine where to go. we need a hash map of ivec2 to, which one of these has we wrote a print grid with a hash map, didn't we? Is that day 14? Yeah, 14 has the hash map print grid. Should just come up with a ton of print grid functions for next year. So back in our part 1, we'll just drop this print grid here. It's not going to be rocks. It's going to be a hash map of ivec2s to plots, right? There's no impl display for plot right now, which is what this would be. So that's going to be an issue. And then here we have parse grid gives us a vec of plots. I think we just take that and we make our hash map. I don't think we need to do anything special there. So in process, we have a grid, right? And we need to, I guess let's do to do return value here, to do find start, to do find end, and then grid map equals grid.iter.map. And this is a plot, and we want plot.span.extra in the first slot and plot in the second, so that we can collect into a hash map of ivec2s and plots. And that's an issue because I haven't upgraded iterm now. I'm not running any of the tests yet. So test day 23, part 1. So we've got value hash map ivec2 plot cannot be built from an iterator over ivec2 reference to plot. That's fine. We can totally use references to plots here. I think even if we wanted to, we could use these as references as well, because everything's going to be referenced. So that's fine. We have a hash map of basically reference to reference. And then what else do we have? Cannot be formatted with the default formatter. So we need to effectively impl display for plot. I mean, not that we have to do this, but plot A, because we have lifetimes, we should be able to implement import display. Yeah, I guess. Implement missing members from Rust analyzer. Wow, my brain blanked on what was causing that. And then this is going to be a match on plot.type. And this is a reserved keyword that we're using there. So we have to rhash it. Oh, because we don't have plot. That's why. It's got to be self.type, and we can fill match arms. And then we're basically going to have 4 of these. 1, 2, 3, 4. Format that. We'll get each of these. I feel like using I guess we can use the characters again. We'll print the characters back out. So we'll select, paste. We've got everything that we could ever want. North, south, east, west, dot. This is the character we have to write. So write FC. Is that correct? I always forget how write works. So in this case, we've written the display for plot and we've reached into the direction. But we could totally have implemented display for direction and then just dispatched out to that here too. Where are we doing this? Iter map. Plot is already a reference, right? So what is the problem with using this here? Value moved here. Oh, and moved in grid. Yeah, okay, that's going to be a problem. There was no actual problem. So debug our grid map and we should get everything. If we print grid, our grid map, I think we need the bounds for that, right? Depending on our function signature, we do need the bounds. We do the bounds every time we do a grid. So we'll just go grab the bounds code, row count, column count, drop that here. And then we'll say let bounds equals ivec2 new, what is it, column count, row count. And then this is a reference to the bounds. And we should roughly get that grid printed back out if we pass in the appropriate reference. Although that doesn't look like it is what it wanted to be. Let's see. Print grid, hash map, ivec2 plot. I guess these are references in our hash map. This is wrong here. So our print grid needs a slight update because these need to be hashes. So this should be the same grid that we are faced with. We basically parsed it in, printed it back out. Looks like it is to me, just a brief scan of the two things. So we can now parse in and print back out the grid. We need to find the starting. So on the first line, right, there's going to be 1, and on the last line, there's going to be 1. So let's do let start position equals grid dot find plot, right? Plot.extra dot y equals 0. Unwrap because we should be able to find that. I need to iter first. Yeah. Some days I wish that like find automatically itered, but then some days I appreciate it not doing that. Plot.span.extra and then end position equals grid.iter.find. It's going to be the same code, so I'm just going to copy it. Plot.extra.y equals row count. I guess we could max here too. Max is probably better. So what? Max by key plot dot span dot extra dot y. I guess this is min, honestly, because of the way we parsed it. No, down is positive. Yeah, down is always positive when we parse like this. I get myself turned around sometimes on that. This is min by key for plot and plot dot span dot extra dot y, right? So we've got start and end. So let's hope that runs. And then we get start position 1 1. No, 1 0. X1 0. Okay. And then 21 22. So that's all the way at the end. 0 1 2 0 1 2 3 4 5 6 8 21. That's correct. 1 2 0 1 2 3 4 5 6 7 8 9 10 22. That seems correct. So we've got the start position and the end position, so we're good to go. So copy paste some code, write a little bit of additional code. We've got the start position, we've got the end position, and now we can actually do our grid walk. Now, the one thing that I do want to look at before we do this is, I think everything in pathfinding is for computing shortest paths, and we need the longest hike, the steps on the longest hike. So I don't think we can use any of the built-in stuff. So we're going to have to probably write this ourselves, which is fine. It's not terrible. I'm just worried about it working for part 2, which I shouldn't be. I should just write it and then do part 2 and find out what it is. This is just any singular path. I kind of wish they had like a generic iteration. Like we've got breadth first, right? It would be nice to have a breadth first. I guess if we're going to do this, petgraph is potentially our option today, because pathfinding only has shortest path algorithms and petgraph just allows us to walk. So here's a breadth first search, right, of a graph. So if we actually build the graph, we can just run breadth first. But yeah, all simple paths returns an iterator that produces all simple paths from node 2, which contains at least min intermediate nodes and at most max intermediate nodes if given or limited by the graph's order. Otherwise, simple path is a path without repetitions. This is just what we want, right? All simple paths, pass in the graph, pass in the start, pass in the end, pass in the min, and pass in the max. This is literally what we want. So let's just build the petgraph today, because I find using things like this to be more interesting personally. I think they were using a digraph in that, which is fine. One thing that's really useful if you are ever trying to figure out how to use a library, for example. So let's say you've never used petgraph before. You're trying to figure out how to use it. You can't quite navigate the docs. There's a lot of types. There's a lot of graph types. There's a lot of type aliases. Can't quite figure it out. If you go to the petgraph repo, it's going to have probably one of two things. The first is an examples directory. And if we look in here, we don't see an examples directory, which is unfortunate. But what we do have is a tests directory. And this means integration tests. That is just a convention in Rust. This is something that is generally true. If there's a test directory, it is testing the integration tests for the library. So anything that's publicly accessible. So if we wanted to build a graph map, for example, right? Here's simple. And this runs a different algorithm, but does that really matter to us? Not really. Is this the way we want to build our map? So this is an undirected graph map. We add some nodes, add some edges. There's a cost to the edges, it looks like. This is a directed graph map test right under it, doing basically the same thing. Removing nodes, depth first search, edge iterators from edges. There's all sorts of different algorithms being tested here. There's custom iteration. There's only one simple, which is the initial build. I forgot if you're zoomed in, you can't use search on GitHub, which is absurd, right? And we can do something like all simple. Is all simple not what we were looking for? All simple paths. Coming in from Advent of Code 2021. Pull requests, commits, code. Code is really what I want. Of course, to use code search, you apparently have to be logged in, and I'm not in this browser. We'll just maximize a Chrome window for a second. We've got all simple paths, all simple paths. Looks like there's no tests, but it doesn't really matter. There is the function in this file right here. There could be a test using it in this file even. So if we build a digraph like this, for example, we have an all simple paths right here as a test in this file. So this becomes a really nice way, either through examples or benchmarks or tests or something like that, to kind of dig into a crate and figure out how to use it, how it's being used, and how you should use it. So let's build up a graph, I suppose. I've used petgraph before. We don't need to do everything like this from edges. So if we look back at, what are we going to use? Digraph. Oh, here it is right there too. See, digraph, add node, add node, add node. extend with edges. We can do a bunch of stuff like that. So let's just pull this in because this is literally what we want, right? And I'm just gonna paste it here, uncomment it, finish uncommenting it because apparently it didn't catch them all. We need petgraph at the top. I'll drop that up here. Petgraph needs to be in here. So petgraph.workspace equals true. We already have our start position. We already have our end position. This is a new digraph, directed graph. They're saying they want string slices to I32s. I'm going to make this IVEC2s to plots, I guess. That is what digraph is, right? If you look at the type signature for petgraph, it's often done as, this is a type alias, first of all, for just a graph. The generics here are node, edge, and index type. We aren't going to change the index type, but the nodes and the edges are for us. So what were they using in that example before I change this? An I32? I think I'm okay with that. It's just going to be one for everything. We have, I think, all of the nodes, right? Which is our grid. Our grid is our vec, a vec of plots. We kind of want a vec of IVEC2s at the moment. So let's do nodes equals grid dot iter dot map plot dot span dot extra collect, I guess. We could just loop over this and insert it a million times, which is not the worst idea. Let's keep it in the spirit of the example, just because I don't see a really strong need to break out of that. And I'm kind of showing how to navigate the docs and stuff. So let's just keep doing that. For node and iter, right? We want graph.add node. It's going to be this plot. And we're going to get rid of these because that's not true. We're going to comment this out for a second. Start position is a plot here. So we're going to do start position dot span dot extra and end position dot span dot extra. So it's important to note when you're working with petgraph here in the way that we're doing it, that add node will return us a node index. And these node indexes are what we need later to be able to run our algorithm. And add edge, it's important to note, will panic if any of the nodes don't exist. So if we're going to do it this way, in the way that the example showed, we're going to need to keep that index to ID mapping. The other thing we can do is build up all the nodes, build up all the edges. The edges are going to be indexed in the same way our nodes are. And then we can use from elements to build up that whole directed graph at the same time. I think I'm actually going to make this the plot maybe for our directed graph. Use plots as the nodes, and then that's okay for our add node. And then for this, we're going to do plot dot span dot extra. Blanked on that for a second. We're going to map over this instead. So we can get a hash map of the IVEC2 positions to the node indexes, which means that when we go to do our edges, we probably want to iterate over this grid map because that'll give us the plot. Although we can also iterate over just the vec that we have, not this vec, not the node map vec. I'm talking about this grid vec up here because this grid vec is just a vec of plots, and those plots all have all of the information we need. So like grid.iter.map plot, and this is going to end up being a flat map because we're going to need to produce multiple from here, because this is going to be, we have the from implementation up here, right? This is just step. This isn't a from implementation. I guess step is what we need anyway. So we'll make this direction north, direction direct south, direction east. If I can type direction west, we're gonna into iter this, I guess, then map over it at some point. I guess this is filter map. We should really match on the plot first, I think. So match on plot.type, right? Because that will tell us whether we have a direction or not. If it's empty, then we need to do this like for place kind of thing. We aren't collecting. I don't know why flat map is giving an issue. Oh, unit is not an iterator because we're returning unit here. So the flat map is like, hey, you can't do that. So if we are empty, then we get all four directions that we can go in, right? So this, and if we are directional, then we only get one of them for each direction, which we already have up here in our match like this. So we'll pull that in. So plot directional in each direction. I guess this isn't even what we need, because if we're just going to do that, we can do this direction. Yes, I can type. And then what? The fixed size array of one element and four elements aren't the same. I don't really want to allocate a vec here, but I think I will for the moment, just to iron that out for a second, because the possible directions logic is all going to be the same. So possible directions, right? So if we take our possible directions, we need to filter map, and this is dir.step plot.extra.span.extra. So the next position is this. That should be an IVEC2. And then we need to check to see if this is a place we can possibly go. So it needs to be a plot, basically. So we have our hash map up here of grid map, right? So grid map dot get next position is sum is really, I think, all we need, right? That's a bool. I think this needs to be a reference, and I think this needs to be a reference. So we've got our next position, which is an IVEC. We've got whether we can move to that position because the grid will only have positions we can move to. If we can move there from where we are, then what we really need is to create the edge, because we're still building the graph here, right? We're going from our current position, which is the plot position, to a potential next position. So match can move here. I guess can move here. That then sum would work. Is then sum a function? I forget. If we go to bool in the docs, then sum will give us a value. I think then is what we want because then is a function. And we don't have to return the sum from this. It'll just work. So this then needs to be the index to the index. So we need the plot IVEC for the index, and we need the next position index, and then we need to weight it. So it's going to be plot.span.extra, right? And this is going to grab our node index. So it's really going to be node map plot.span.extra. And this is going to be node map next position. And this is going to be 1. And then that's a filter map, but this is a flat map. And then plot span extra probably needs to be a reference. And then node map is not a function. I don't know why I did that. This also needs to be 1. And then we probably have lifetime issues. Cannot return value referencing local variable possible directions. That makes total sense because we constructed this array in here. And no matter what, we have to construct like at least one of them. We don't have to per se. Like we could run this logic in both of these branches and it wouldn't really matter. It wouldn't affect us that much. We would just need to move that code in. And then because possible directions is local to the flat map closure, we can't reference it later. So like, first of all, we have to own those values, right? We have to take them with us. So into iter helps us out there. I think all of this turns into the edges, right? If we've done everything correctly, at which point we can do graph extend with edges. And if we haven't done everything correctly, it'll tell us, oh, we didn't collect at the end. So collect, we'll collect this iterator. Oh no, we don't have to, I don't think. I think adding edges to and from any position that can is okay because we won't traverse along them anyway. So we should be able to just add the edges like that. I don't know that I saved the graph. There's the graph. All right, so we've got a bunch of plots. This will let us dot graph it out. And the dot graph, of course, lets us do whatever we want. So let's pump out a dot graph here. I think I want to write this to a file now that I think about it, because this is going to be a decent amount of stuff. Let's see if it fills the terminal history or not. Yeah, it fills the terminal history, so we kind of have to write it to a file. So instead of print line, we can do, I guess this is dot dot, right? Dot dot. It's going to be this. I want to format this though with the debug formatter, which I need to close the parenthesis on. We need to bring in standard FS file. We need to write out as bytes. Write all is probably not in yet. Yeah, there we go. So all of that to say that cargo next test really wants to keep firing off there. All that to say we have this dot graph, which the labels are a little bit wonky. And if we drop this into a GraphViz viewer, which I think I have one in VS Code actually, now that I think about it, then we get this massive thing here. And we can see from, can I download this as maybe PNG? There we go. Hopefully this PNG is going to be big enough. Yeah, so we can zoom in here. It's a really awful zoom, but you can see here that we've built our graph and technically we can go from any to any, right? But we've got this starting position up here at 1, 0. 1, 0 can go to 1, 1, can go to 2, 1, can go to 3, 1, can go to 4, 1. So that should match up. I'm going to comment this out because we've already kind of written that out. That should match up with this, right? So 1, 0 can go to 1, 1, can go to 2, 1, can go to 3, 1, can go to 4, 1, and so on. And it shouldn't split until here, I think, if I'm looking at this correctly, which is 0, 1, 2, 3, 4, 5, 4, something like that should have a choice in it. 5, 3, whatever, same thing. 5, 4, and 3, 6. So 0, 1, 2, 3, 4, 5 is actually 4, 5. So it's 5, 5, and, or 0, 1, 2, 3, 3, 5, 4, 5, and 3, 6. Is that the right? 3, 5, 4, 5, and 3, 6. Yep. So that's our split right there. We can see it now. .viz, we can also very likely actually condense this entire graph. And I have a feeling that that's what we need to do in part 2. So that'll be fun because technically condensing this whole graph means that we only really have 5 nodes, but we still need to run part 1. So we still need to actually do this. We need our node indexes. So we've got start position, right? And I think this is node map, if I remember correctly. Node map, start position, span extra, probably a shared reference. Same thing for end position. And then this should just give us the max. So what if we run max by some function, right? And it's really the length function. That gives us an option node index. I guess we have to into iter here. Is that the, all right, this is, hey, Chris, start actually looking at the compile message. Closure takes 2 arguments. What were we collecting into before? I thought we were collecting into a vec. Oh, this is A and B. A, B, A.length, .comp, B.length, right? And then we don't need that collect. Ways is going to be our option of vec node index, which I guess we need to write one on. So unwrap this because we expect it to work. And then ways dot length is, I think, our answer. So let's debug that out and we'll also use it in our response. Get rid of the type inlays, leave all of our nice comments. And then this says 94, write 95. Do we need, so we have 95. So this is not including the start position. I assume it's not including the start position or something like that. So I'm going to be okay with this. Maybe it is the other way around. Let's take a look at the paths documentation. Returns an iterator that produces all simple paths from node to 2, which contains at least this and at most that if given, or limited by the graph's order otherwise. This is a simple path without repetitions. Doesn't tell us whether we are including, 94 steps. So from one to another is a step, right? That would make sense. Because then 95 positions, if you step from 1 to 1, right? Like if we're going to get here, which is 3 positions, then 1, 2 steps. Okay. So we actually need this to be -1. I'm going to leave a comment here that's basically like step count is tiles visited -1. And that's good. And then we run this, hopefully. I'm still running my visualization from day 22. I turned that into an actual game, which I'm going to release on itch, I think. I forgot we were dumping that out in print grid. That's right. Gold star. Yay, us. And now we have to do that a million bajillion times. As you reach the trailhead, you realize the ground isn't as slippery as you expected. You'll have no problem climbing up the steep slopes. Now treat all slopes as if they were normal paths. You still want to make sure you have the most scenic route possible, so continue to ensure that you never step on the same tile twice. What is the longest hike you can take? In the example, this bumps up to 154. So it's going to be the same thing. And I'm going to hope that because we're using indices here and we used references for all of our graph content and stuff, that this will be lightweight, but I don't know. Let's get rid of the print grid, wherever that is. I think those are the only 2 debugs that we have here. Yeah. And we didn't need bounds because we're not using print grid right now, but that's fine. So let's run part 1 and see what that does. Cool. If we bench part 1, we should panic on part 2. So not especially fast. 11 milliseconds to run this. Don't know where all the time is going currently. And then our DAP profile, I did a cargo clean, so I have to reinstall everything. 6 megabytes. Would be interesting to look at this and see where we're spending. I think I'll wait on that though. I'm going to take this all, I'm going to put it into part 2. We've got some, this is 154, right? We've got some new logic here. This is really easy for us, I think, because now possible directions is just always this vec. So ta-da, we've fixed our logic for part 2. Let's run our test for part 2 and hope it runs. Test passes, it looks like. Again, we never saw it fail, so whoops. So running part 2, I have no idea how long I'm supposed to expect this to run for. And we did allocate 6 megabytes for the other one. So if we look at this, it's not like we're parallelized or anything. There we go. Memory, 4 megabytes. That doesn't feel bad at all. I'm not running, okay, I'm running Photoshop, but not like DaVinci or anything. So I think I'm just gonna let this run for a second. I feel like mostly because like our memory usage isn't that high. And I don't know offhand of a way to speed up the actual algorithm if we do actually need to run everything like we need to do. Because we need to find the longest path. So the only thing that we would be able to cull is the very last length. We could condense our graph, but I don't know that that actually helps us. Depends how big our input is, I guess. So if we look at the graph dot stuff, right? Or we look at the actual input, it doesn't really matter which one we look at. But we get this path here, and this is not a path that we can even have a choice to get off until, wow, until here. We have to travel like 100, I don't know, it's not 100, but we have to travel quite a bit before we even have a choice. So if we condensed the graph then, I think we could get it to condense to only the decision points because everything else wouldn't matter. And then theoretically that could run faster because we wouldn't be, you know, processing 27 times for every branch of things that we can't even. So I guess it really depends on whether petgraph is doing anything for us behind the scenes. Still running at 4.8 megabytes though. I know a lot of memory is being used on my computer, but we still have, maybe I should quit Photoshop. Okay, it looks like this is gonna run. And when I say run, I mean really just run. Okay, so it stopped after 9 minutes and 30 seconds. We submit this, and that is the correct answer. So we're good. So yeah, we're done. I'm not benchmarking a 10-minute runtime, but it's 10 minutes or 9 minutes and 35 seconds this time. I actually don't know if condensing the graph would even do anything for us. I might try that, but let's go into the deep dive because we already know what the numbers are. We already did the benchmarks, and part 1 and part 2 are the same thing for us. So this is going to be one giant deep dive with a small part 2 mention at the end. I guess let's leave in the things I'm not using here because I just commented them out rather than actually removing them. I think I'm going to leave them here because I want the dot stuff to be here for people to see. So that brings me to the most stars I've ever had in Adventure Code, which is fun. I need 5 more. One is day 12, part 2, and the other 4 are tomorrow and the 25th. So the 23rd is a long walk. We get this grid. We have to parse this grid out. We have, to start with, a bunch of dots and arrows that represent either places we can go anywhere from. So all of these are places we can go anywhere from, all the dots. And the arrows mean that if we're on them, we have to go to the right or we have to go down or whatever. Kind of like a 2D arcade game, right? Where you go over a little like boost pad and then you have to go that way. We can't double back. So we can't be like going down this way and then coming back this way and then going down. We can't double back, which is great. And then we have to find the longest path through this maze. So shortest path, tons of algorithms to do that. Longest path, I think we're just stuck with calculating it all. So today's big winner was the all simple paths algorithm from petgraph. This is our first usage of petgraph this year. And I think that it's required compared to all the other ones. Usually you can use pathfinding. Pathfinding doesn't have like an all paths function. So I think you might be able to like work it in there, but I don't think it's going to be any better than coding it yourself. Petgraph, however, if we build up the graph, we get the benefits of kind of being forced into a certain direction here. So we've got the weights for the nodes, right? And things like that, all the information on the nodes, but all of the nodes have IDs. And we're kind of forced into the nodes having IDs because of the way petgraph works. It more or less forces you into, let's go to the graph thing here somewhere, graph. So the graphs in petgraph tend to use like indices into another data structure, which is fairly common for like cyclical or self-referential or graphical data structures in Rust. So what we end up with is this graph, but it's backed by effectively a hash map. Now, is it actually a hash map? Not necessarily. Here's a vec of nodes and here's a vec of edges and whatever. But it's backed by other data structures is kind of what I'm getting at. And we're indexing into those data structures. So once we build those data structures up, we're kind of just using those indices. And those indices have relationships, which really forces us into this pattern of using these indices when doing processing. Because we know we have a bunch of nodes. We know those nodes have edges and we know they have weights. So the TLDR here is that petgraph is probably the most well-developed graph library in the Rust ecosystem right now. And it forces you into good design patterns for this kind of data, which really paid off for us when we went to run our actual algorithm. Yes, it did run in like 10 minutes. And I haven't looked up what everybody else's runtimes are currently, but I know some people's runtimes and they are longer than the petgraph runtime. And we didn't think about performance at all. So for me, that's a huge win. Indices allow us to do things like mutate while traversing the graph, which we didn't need to do today, and other complicated things like building up multiple graphs where all the nodes are the same IDs and things like that. And of course, there are some trade-offs, but overall, petgraph kind of forces us into doing the right, quote unquote, right thing here, which means that all simple paths takes the graph, takes the node ID that we're trying to go from, and the node ID of the node we're trying to go to, some bounding conditions if we need them. In our case, everything is finite, but if we had an infinite grid for some reason, we could cut this off. So the first thing we do is parsing, as usual. Get the row count, the column count, we build the bounds. We don't actually use these really. And then we parse our grid. Our grid parser is the same parser we used on, I think, day 16, if I remember correctly. It is a fairly verbose parser. This could be written in a more concise way, but it gets the job done. And it was basically copy paste from our old implementation. We've got this plot type struct that is either empty, which represents the dot, or a directional, which represents one of the cardinal directions, north, south, east, or west. We already have a function from one of our previous days that allows us to take that position and add one of the unit vectors to it. So either north, south, east, or west. So that gives us this plot type. Plot contains that plot type that we just talked about, and we keep around the span and the IVEC2. Kind of just keep this around for debugging purposes. We could just have kept the IVEC2 and the plot type, but I like keeping around the actual character we got just in case. We implemented display for plot for a print grid. We've done this in previous days, same thing as usual. Implement display, let Rust Analyzer write this format type signature, which is the type signature you have to match. And then the write macro is what you need to use. So you pass the F, the formatter in, and then you pass in your formatting string and you pass in any things that go into that formatting string. So all that together means we get a grid. We get a vec, that is, of all of the plots. We turn that into a grid map, which is a map from IVEC2 to plot. We get the start and the end position by doing min and max on the Y values. Then we start building our graph. So we use a directional graph, although we really didn't need a directional graph per se today, because every node ends up getting a relation back and forth from the other nodes, but we'll ignore that. Our node type here is plot, and our index type is an I32. I think we could just do that as well. I think the default is U32 if I remember correctly, which also doesn't cause us any issues. So like we could use U32. We could also break this down and do like a U16 and make a smaller sized graph. But all things considered, we don't really need anything in particular special here. So we start a new graph. We build up a node map from IVEC2 to node index. So this is the second map we've built up. We iterate over the original grid. This is our vec, and we flat map that. This overall is to build up the edges. So we just added the nodes here, right? So when we built up this IVEC2 to node index, we needed to have the node index. So we took this graph that we just built, we added the plot as a node, and we keyed it in our map by the IVEC2. So graph add node returns the node index. We key it by the value that we want to get it by, and we can get the node index by IVEC2 using this hash map. Then we take that grid again, we flat map over all the plots. For each plot type that is directional, we can only move in one direction. For each plot type that's empty, we can move in any of 4. We then need to filter out anything that is a brick or a block. Remember, this is building up the graph, not traversing the graph. So this is just picking the locations that we could go, not actually doing the traversal right now. So we step in a direction using our IVEC unit vectors. We check to see if we can move here. If it's in the grid map, we can. If it's not, we can't. If we can move there, then we grab those values from the node map being these node indices. So we have the from node, the to node, and the weight. The weight for us doesn't really matter in this case. They're all just 1. So this setup right here gives us what we need to add the edge. We've got the from node index here, the to node index there, and the weight of the edge. We add that edge, and we have our graph built. Once we have our graph built, we just run all simple paths on that graph with the start node index, the end node index, the min value, and the max value for the path length. That gives us back all of the options. So we run max by on the length comparison to pick one of them. Eventually that comes out, and what we end up with is the longest path right here. We then take that longest path, we subtract 1 because we're looking for the step count and not the tile count, because the step count of a 2 tile sequence is 1. And that's it, we're done. We also implemented a dot grid layout here, or a dot grid printout. That gives us this dot graph visualization that we can then take either to a VS Code extension or the internet, and gives us this graph here. This graph I will probably include manually in this video because scrolling around on it manually is kind of awful to look at. I don't know. You may have seen me scrolling around on a white map. You might not have. But this dot grid output is really nice. One thing we could do from looking at the dot grid layout is we could condense the grid. So if we look for condensation, we got petgraph algo condensation, condense every strongly connected component into a single node and return the result. This might or might not help us. It is mostly for cycles. So in this case, we have 2 cycles in B to E, but we do have these long paths of singles, right? So we have these like very long towers of one path, and then we split once, and then very long towers of path, and then we split once. So we might be able to speed something up by getting rid of some of those, whether it's through condensation or it's not, and we just build the graph up the way that gets rid of those. But in part 2, our part 1 works just fine. The only big difference that we make, or the big change that we make here, is when we do our directionals, we no longer care if we're on an arrow or not. So we do 4 for everything. And then this just runs the same way it ran in part 1. It runs for about 9 minutes and 35 seconds. So there might be a faster way to do this. I don't know, but I'm fine with this for today. It was very quick to make that one change and just have a solution that ran and ran correctly. So I'm happy with that. And that'll be it for today. We've got 2 days left. We still have 1, 2, 3. Still got a few people hanging on here, doing every day. Hey, I'm on here. Recognize FoamX from Discord, recognize a couple other people, Gold Armor. Our top 3 have been basically the same top 3 all month. Of course, this is an early look kind of at it because we are 2 hours after the event started. So I expect this to fill out a little bit more. I had my own personal best time today after having my personal worst time on day 21. I think that's my worst time anyway. I hit 1075. I'm not really a competitive person when it comes to this, but you still get that dopamine boost. So that's it. It is the 23rd. We've got 2 more days. We've got the 24th and we've got the 25th. So if you've got any other stars to pick up, I've got day 12 part 2 to pick up. I'll be doing that tomorrow in the morning. And that's it. If you're still hanging in there, congrats. It's been a long one this year, and I will catch you in the next video. Have a great rest of your day.